If you've ever watched a flight tracker and wondered, why does my flight arc way up toward Alaska instead of going straight across the Pacific? You're not alone. There's a viral idea that airplanes avoid the Pacific Ocean. Here's the truth. Airliners cross the Pacific every single day. The real story isn't that they don't fly over it, it's how and why they choose specific paths across it. Today we're busting the myth and unpacking the actual reasons airline routes look the way they do. Map illusions, wind and weather patterns, safety rules, emergency planning, and the economics that drive those elegant arcs you see on the map. Let's start with the biggest misconception, the map itself. On most maps, a straight line looks like the obvious shortest path, but Earth is a sphere. On a globe, the shortest distance between 2 points is called a Great Circle Route. On a flat map, that shortest path often looks like a curve. So when you see flights curving over the North Pacific or skirting Alaska, you're not seeing a detour, you're seeing the shortest path rendered on a flat map. Los Angeles to Tokyo, Seattle to Seoul, Vancouver to Hong Kong, the shortest Great Circle paths arc north toward higher latitudes, then back down. They're shorter in miles, save fuel, and cut time. So point one, planes absolutely do fly over the Pacific, constantly. But they rarely fly straight across the center of the map because straight lines on a Mercator projection aren't actually straight in 3D space. Now the wind. High above the Pacific, powerful rivers of air, the jet streams, flow west to east. Eastbound flights from Asia to North America often ride these tailwinds to go faster. Westbound flights typically avoid them to dodge time-sucking headwinds. Those invisible highways can add or subtract hours. That's why your Tokyo to San Francisco flight might follow a different track than the San Francisco to Tokyo leg. The routes are dynamic. Airlines and air traffic control publish daily tracks across the Pacific, optimized to take advantage of the winds that day. Think of them like moving lanes in the sky. These tracks shift with the seasons. In winter, the jet stream strengthens and moves south, so eastbound flights swing into it. In summer, it weakens and shifts, and the tracks move too. The route you see is part wind strategy, part shortest path, and part safety calculus. Speaking of safety, let's talk ETOPS, Extended Range Twin Engine Operational Performance Standards. It sounds technical because it is. In simple terms, ETOPS sets the rules for how far a twin-engine jet can be from a suitable diversion airport in minutes of flight time if something goes wrong. Modern jets, Boeing 787s, Airbus A350s, are allowed long ETOPS ratings, like 180, 240, even 330 minutes. That means they can legally fly routes where, if one engine failed or the cabin suddenly depressurized, they could still reach an alternate airport within those time limits. Operators plan specific equal time points, the exact moment where turning back or pressing on to the next alternate takes the same time. They plan for multiple scenarios, engine failure and a lower drift down altitude, or a rapid descent due to depressurization, which means higher fuel burn in different speeds. Here's why this matters. The North Pacific has a chain of alternates, Anchorage, Cold Bay, Adak, Semya, and more, like stepping stones. The Central South Pacific, much sparser. You've got Honolulu, Midway, sometimes Wake, Guam to the west, and farther south, Tahiti, Easter Island, Fiji, Rarotonga, Auckland. But the gaps can be hundreds of miles. That sparse safety net shapes routes. Historically, fewer alternates and lower ETOPS ratings nudged flights along the northern arcs. Today's long-range jets can and do cross the deep Pacific, Sydney to Santiago, Auckland to Buenos Aires, when operated, Los Angeles to Melbourne, but every oceanic route still has to respect diversion times, forecast weather at alternates, runway lengths, volcanic ash advisories, and rescue considerations. Beyond jet streams, weather drives routing too. The Intertropical Convergence Zone, the ITCZ, sits near the equator, a band notorious for towering thunderstorms and turbulence. Typhoons in the western Pacific can balloon across airway corridors, forcing detours. And volcanic ash, common along the Aleutians and parts of the western Pacific, is a no-fly hazard. Even tiny ash particles can sandblast engine blades and flame out turbines. When VACCs, Volcanic Ash Advisory Centers,
flag an eruption, routes shift fast. There's also solar activity at high latitudes. Strong geomagnetic storms can disrupt high-frequency radio and satellite comms, degrade GPS accuracy, and trigger temporary reroutes away from polar-adjacent paths. Over the mid-ocean, there isn't continuous radar coverage like over cities. Instead, aircraft use satellite-based systems, ADS-C for position reporting and CPDLC for text-like messages with air traffic. Controllers separate airplanes by time, altitude, and lateral spacing on those daily tracks. That lower resolution compared to dense radar environments is another reason airlines tried to pick efficient lanes and stick to them. Predictability equals safety and fuel savings. So while the sky looks empty, oceanic airspace is highly organized, more like an invisible highway system than a free-for-all. Airlines live on thin margins. Even with the shortest path, wind, payload, and cost can change the equation. A route with stronger headwinds might burn so much fuel that a longer Great Circle alternative winds up being faster and cheaper. Add in weight limits, full cabins, freight, fuel reserves, and sometimes flights take a slightly longer path to enable a higher payload and better on-time performance. There are also overflight fees and geopolitical realities. Access to certain airspaces can shorten or lengthen routes. In recent years, restrictions over Russian airspace have forced some carriers to swing farther south on certain Asia-North America pairings, while others with access can still use more northerly corridors. The point is, routes adapt to a moving target of winds, rules, and real-world constraints. Example 1. San Francisco to Tokyo. On the way west, you'll often arc up past the northwest coast, across the Gulf of Alaska, and down toward Japan, staying within good alternate coverage and minimizing headwinds. Coming back east, you might dip slightly south to grab tailwinds, arriving faster than the outbound leg, sometimes by an hour or more. Example 2. Sydney to Santiago. This one dives deep into the South Pacific. No Alaska shortcut here. It's a long overwater segment with sparse alternates. Airlines use high ETOPS approvals and carefully chosen alternates like Easter Island and Tahiti, planned ETPs, and stringent weather minima. It's a perfect counterexample to the myth. Yes, they fly over the deepest Pacific, safely and routinely. Example 3. Los Angeles to Hong Kong. Depending on season and winds, you might see a far northern route skirting the Aleutians and Kamchatka, or a more central Pacific path. After 2022, some routings changed to avoid closed airspaces, illustrating how geopolitics can reshape the map overnight. So if they do fly over the Pacific, why do we keep seeing that distinctive swoop over Alaska? 3 reasons. Great Circle geometry. It's literally shorter on a sphere. Winds. The best tailwinds and least headwinds live at higher latitudes. Alternates. More emergency landing options along the North Pacific Rim. Put together, those factors produce routes that look curved on a flat map, but are actually the smart, safe, and efficient choice. A final word on safety. Oceanic flights are layered with protections. Aircraft prep, additional maintenance standards for ETOPS and EDTO, redundant systems, extended fire suppression endurance, life rafts, ELTs, survival gear. Crew planning, multiple diversion scenarios, ETPs, fuel for contingencies, and performance calculations for engine outdrift down over cold water or terrain. Operational control, dispatchers and flight planners monitor winds, storms, ash, satellite comms, and alternates along the entire route in real time. Traffic management, organized tracks, altitude stratification, and mandatory reporting for precise separation. This isn't point at west and hope for the best. It's an engineered, constantly monitored system. So the next time you watch your flight path curve like a bow across the top of the world, remember, that elegant arc is the product of geometry, meteorology, safety engineering, and economics, working together to get you there faster and safer. It's not that planes don't fly over the Pacific, it's that they fly the smartest possible way across it. Window seat or aisle, now you know why your map doesn't tell the whole story. Safe travels. Subscribe and turn on the notification bell so you don't miss out on any of our videos about aviation.